start recording. So the subject will be the degree of freedom. Now, but before the degree of freedom, I showed you certain mechanisms. The mechanisms, when they are used in machines, they might look very complicated, but we usually simplify them. A real mechanism, for example, to open a close a window, looks like this in real life. This is the engineering drawing, but the mechanism drawing is a very stripped down or simplified version of that, so that we can understand the essentials better. Okay, so what we really have here is something like this. Okay, in which we have a crank, and there is the crank is hand operated, I guess. The one is here. The second link is here. The third link is something that can move with respect to the fourth link, etc. Now we simplify it and make a mechanism of this kind. Now, in these mechanisms, there are certain conventions. As I have said, the first link is always the ground. The prismatic joints are shown by a piston kind of a joint. And this kind of, let's say, box shows that the fourth link is continuous. Okay, so here you have a revolute joint between the fifth link and fourth link, but you don't have a revolute joint between this part, which I'm showing now, and that part. This part is like a welding, you might say. Okay, if you don't put this part here, you might think that there is a revolute joint between this part of this link and that part of this link, which is not the case. And here we have again a prismatic joint, for example. So the kinematic diagram and the engineering drawings are different. Well, they are related, but they are different. The kinematic diagram is very much simplified. For example, if you have a piston, if you have a hand press, the real drawing of the hand press kinematic diagram of it is something like that. It is essentially, for our purposes, for the kinematic analysis, these two things are the same. Here we have a prismatic joint. Here the arm is modeled by a triangle here. This thing is the third link. This one is the fourth link. And there is a joint, two joints here, two revolute joints connect here. There is a prismatic joint that moves up and down. And also, if you have something like a hydraulic piston or pneumatic piston, if we replace it by a sliding joint moving on a rotating joint, kind of. Okay, so this is a prismatic joint moving on a joint that can rotate. This is usually how we model a hydraulic device that can rotate, as you see. Okay, again, a hydraulic actuator is modeled here. We will see that a triangle like this can be modeled by, is a single link. Okay? This triangle does not have a, even if it has revolute joints, It doesn't have a degree of freedom on its own. We will see that. Here, this thing means that there is welding here, so that there is no joint between this part and that part of the link. And this is a hydraulic actuator. Okay, and this thing over here is that you have a fixed angle. That is the angle between this part, A0A, and A, whatever, B or C. This angle does not move, change. For example, this is this angle we are showing here is fixed. It doesn't change. So we show that by putting a kind of a welding over there again. Okay. And again, this thing we put there indicates that the fact that you have a rigid link. So these are the conventions used in the kinematic diagrams. So I wanted to talk about these. So we come to degrees of freedom again. So we will briefly talk about that. There is translation. The degrees of freedom in three-dimensional space, as we have said, we have three translations and three rotations. Just a second. Three translations and three rotations. So in the plane, you have three rotations. This is a nicer way of showing it. So in the planar mechanisms, this I have explained before. You have 3 degrees of freedom for a 2D mechanisms. So if you have L links, okay, if the number of links is L, the degree of freedom of the mechanism, if they are not connected at all, with no joints, you have 3L degrees of freedom. Okay. Usually, by the way, when we count the number of links, we count the ground link as one link as well. We will come to that. Okay. Now, this is the same thing as we have done in the previous lecture. The lower pairs and the higher pairs. The lower pairs, as I have said, are revolute and prismatic, and these are gears, cams, rollers, etc. The revolute joint is the simpler pair, and its degree of freedom as a joint, degree of freedom of a joint, what we call F for the revolute joint is 1. Okay, as one of your friends said, if the other link is fixed, it allows 1 degree freedom to the other link. Okay, that's why we call it the degree of freedom of that revolute joint as 1. The cylindrical joint, this is another one. Cylindrical joint allows 2 degrees of freedom to the connected joint. This is a 2 degree of freedom joint. In which case you have a prismatic joint, but also a possible rotation there. Okay. So this is a cylindrical joint. C has 2 degrees of freedom. Prismatic joint has 1 degree of freedom, as I have said. This is spherical. This is a 3-dimensional joint. A sphere, a spherical joint, allows 3 rotations to the joint to which it is connected. It is like a ball and socket joint, so that one of the links that is placed in the other one can rotate freely, so that in all 3 directions. So it has the joint has 3 degrees of freedom. This is helix. It is very similar to the cylinder, but the rotation and the translation are dependent on each other, so degree of freedom is 1. There is the so-called the planar pair. This is not very much used, but it is there. So, okay. Let's talk more about the 2 degree of freedom joints. If there is rolling and sliding between 2 points, that joint allows 2 degrees of freedom. If it is rolling without sliding, with no slip, that is, in that case we have rotation and translation are coupled to each other. We have, as you remember, x is equal to r theta is given here. So the degree of freedom of the rolling contact is 1. This is kind of important. The gears, between the gears, there is sliding and rotating motion between the teeth. So that in the gears, you might think that there is 1 degree of freedom, but actually, in the actual case, the degree of freedom of the gears is 2. Gear, let's say, gear joint. If you have a gear joint, the degree of freedom of the gear joint is 2. It is a higher order pair. We will see this is a little bit counterintuitive in the beginning, but we will see why we do that. Belts and pulleys, if they have no sliding, or chains and sprockets, when there is no slipping again, the degree of freedom is 1. When there is a spring, the spring actually means nothing in the mechanisms. Springs are in the mechanisms, they are in our, for our analysis, for the degree of freedom analysis of the mechanisms, the springs are not counted at all. Just keep that in mind. Okay, now we talked about degree of freedom of a joint. Degree of freedom of a joint was explained by degree of a joint, the degree of freedom of a joint, which we talked about until now, is what we call F. Okay, for example, for R and P, F is 1. Now, degree of a joint is something else. If you have, for example, if 2 links are connected to a revolute joint, like this one, 1 and 2, you have a binary joint, because binary means 2. If you have 3 links connected to it, you have a ternary joint. If you have 4 links connected to the same joint, you have a quaternary joint. This is not too important, but it shouldn't be confused with the number of the degree of freedom of the joints. In the actual case, here you have only 1 revolute joint. Here you have not 1 but 2 revolute joints, because you connect 1 and 2 and 1 and 3 to each other. Okay? Well, 2 revolute joints connect these things, and here you have 3 revolute joints, for example, connecting the links. So the degree of a joint and the degree of freedom of a joint are 2 different things. That's what I wanted to emphasize. Now to make things a little bit more complicated, now we talk about the degree of freedom of a mechanism. Degree of freedom of a mechanism is a mechanism when all the links are connected to each other. You have a mechanism. You see, here you have a 4-bar mechanism, as you see. The 4-bar mechanism in which the first link is the first link, second link, sorry, third link and the fourth link are used. They are connected to each other by revolute joints. There are 4 revolute joints connecting to each other. Now this mechanism, its position can be specified exactly by specifying only one parameter, and that parameter might be this crank angle theta. Okay, so only one input is needed for this mechanism to uniquely specify position of all points in the mechanism. So the degree of freedom of this mechanism is 1. So the degree of freedom of a mechanism is the number of independent parameters required to define position of every link in the mechanism. Okay? For example, for the 4-bar mechanism, it is 1, which also means that only one motor, only one prime mover is needed to drive this mechanism. In order to uniquely specify the position of the mechanism, you just need to attach a motor to link 2. If link 2 rotates, and the links 3 and 4 will make specified motions. So the degree of freedom of this mechanism is 1. This is a 4-bar mechanism. On the other hand, if we have a 5-bar mechanism, for example, like this one, the 1 being the ground, 2, 3, 4, 5. We have added one more link, this purple link, to this mechanism. Now we have 5 bars. Now the position of these mechanisms cannot be uniquely specified by theta only. We need 2 inputs or 2 coordinates to specify the position of this thing. So the degree of freedom of this 5-bar mechanism is 2. Okay. So it's a bit confusing, but I think we have made some progress. We talked about the degree of freedom of space, degree of freedom of the links, individual links, degree of freedom of the joints, and finally the degree of freedom of the mechanism.
Hocam, sorry, can I ask a question?
Yes.
Is it possible to design 4-bar mechanism with more than 1 degree of freedom?
No, the degree of freedom of a 4-bar is 1. Not do anything about that. The links we assume that the links are rigid. If you assume elastic rings, if you make links elastic, like vibrating or whatever, you might have more degrees of freedom, but the 4-bar mechanism is uniquely specified by one input. But if you have 5-bar, as you see over here, 5-bar mechanism has 2 degrees of freedom. It can be specified by 2 inputs, like theta and phi. But the mechanisms we are going to be studying will always, at least in this course, will always be 1 degree of freedom mechanisms, because you usually have one input and you want to generate an output motion out of that input, okay? Or transmit force from that input. 2 input mechanisms would be usually too hard to deal with.
Thank you, hocam. Thank you.
Okay. Actually, the multiple degree of freedom mechanisms, for example, robots are multiple degree of freedom because for each arm you have a motor connected to each arm. But of course, these are require precise control and controllers to control the motion. Whereas for mechanisms like a 4-bar, you don't need a controller or a control computer to generate the motion. Okay? It's uniquely specified. It doesn't need anything. You just connect the motor to it and rotate it. So the degree of freedom of a mechanism which we will call the capital F, okay, depends on the degree of freedom of the space, which is called lambda, which might be 3 or 6, okay. For 2 dimensions, it's 3. For 3 dimensions, it's 6. Degree of freedom of the joints, you can have F equals 1, F equals 2, F equals 3, etc. Okay. Number of links and joints in the mechanism. Yes, we will talk about that. The links and joints, we have to count them. And how these links and joints are distributed. But then the shape of the links is totally irrelevant, or the length of the links is irrelevant to the degree of freedom of a mechanism. Okay. So I think we are approaching. Let's see how we can go on. We will say that the degree of freedom of space is 3 for two-dimensional space, for T through D, or lambda is equal to 6 for three-dimensional space. Okay. Now the number of links in the mechanism, and we include the fixed link as well, as you see. For example, if you have a 4-bar, let's say, like here, this is another link. 1, 2, 3, 4. These are all revolute joints. It's 4. The number of links in the mechanism for the 4-bar is, for example, L is equal to 4. Okay. 1, 2, 3, 4. We have counted them. For the joints, number of joints is J. You have 4 joints, which are all 4 of them are revolute joints. Okay. And F is degree of freedom of all joints. We have 4 revolute joints, so F equals 1 for all joints, let's say. And F is the degree of freedom of the mechanism. What is the degree of freedom of the mechanism? We want to find out that out. Now we will do an argument like this. For example, we have 4 links here. If you have 4 links, what is the degree of freedom of 4 links without any joints at all? Well, each of these links, where is that? We didn't count the first link, but 2, 3, 4. We need the ground link also. We have to put that into here. 1. Therefore, we have 5 things here. How many degrees of freedom do we have here? For each of these links, we have 3 degrees of freedom. So we have the degree of freedom is 12 here. Okay. So in order to describe the motions, we need 12 parameters if these things are not connected by any joints. If you connect them by certain joints, now the joints decrease the degrees of freedom. For example, link 2 is connected to other links now. Link 2 by itself still has 3 parameters, okay, to describe its motion. Link 3 is connected by a cylindrical joint in which it can move with respect to link 2 in this direction. It can also rotate with respect to link 2 in this direction. So it has still two more parameters. Okay. Link 4, where is this one? Link 4 is connected by a revolute joint here. It can only make a rotation, so it only has one parameter now. Two of the rotations are restricted. And link 5 can also only rotate with respect to link 2. So it also has one parameter. So we have, with these 3 joints, 1, 2, and 2, we have constrained 5 degrees of freedom now. In the beginning, we had 12 degrees of freedom, remember? So we have constrained 5 degrees of freedom. Now the degree of freedom is reduced to 7 now. If you connect them in the following fashion. Is this understood? Is this clear?
May you explain it again?
Okay.
The 3 joints is
You have 12 degrees of freedom when they are totally unconnected. Right? This picture you understand. There are 12 degrees of freedom. And we decide to connect them to each other like this. One cylinder in the slot joint. Here, between 2 and 3.
yes, hocam.
And then you have 4 is connected by a revolute joint, R. This is cylindrical, this is R again. Okay. Now, with respect to 2 itself is not constrained by anything. 2 is free, so 2 has 3 parameters already. So link 2 has 3 degrees of freedom. It's not constrained. You understand?
Yes.
Link 3 is connected to 2 by a cylindrical joint, and the cylindrical joint constrains constrains one parameter out of this. It has 2 degrees of freedom. So it allows 2 degrees of freedom to link 3, constrains 1 degree of freedom. 4 constrains 2 degrees of freedom. And link 5, this revolute joint constrains 1 degree of freedom. This revolute joint constrains 2 degrees of freedom out of link 4. Because it can only now rotate with respect to link 2, and there is no other motion. Now link 5 can only rotate with respect to link 5. Okay, so here you have 5 degrees of freedom are constrained. This is the cylindrical joint, the revolute joint, and the revolute joints have constrained 5 degrees of freedom. So we have begun with 12 degrees of freedom. Now 12 minus 5, we are reduced to 7 degrees of freedom now.
Hocam, I think I skipped the part, so the link 4 can just only rotate around the cylindrical joint, right? So it has just 1 degree of freedom.
Yes.
So what is the 2 degree of freedom in plane motion.
What do you mean?
Like it
I
said,
don't
you
understand
know,
what you mean. What is the? I mean,
oh, I'm sorry. So it is just an explanation, right? It's not only for link 4. Like revolution joints has 1 degree of freedom, constraints 2
yes,
degree of freedom in plane.
yes,
Okay.
this thing can only rotate like here. Okay, respect to 2. Do you understand that?
Yes, hocam.
So the degree of freedom of this mechanism connected in this manner is reduced to 7 now.
Okay.
So a joint constrains if the joint degree of freedom is Fi, a joint constrains lambda minus Fi freedoms. For example, here, this joint, which is a cylindrical joint, has a excuse me. What can I do here? Okay. This F is equal to 2 here. So the constraint the degree of freedom is 3 minus 1. Sorry, 3 minus 2 is 1. So you constrains 1 degree of freedom. Whereas the revolute joint has a R has a F of 2, so it constrains 3 minus 2. Sorry, 3. I'm tired. 3 minus 1, 2 degrees of freedom. Okay. So in general, if a joint has a degree of freedom of Fi, it constrains lambda minus Fi freedoms. If you have J joints, in general, you have the summation of these, which is lambda times J. This is a capital J. Lambda J minus Fi freedoms. So we have constraints lambda J minus sigma Fi freedoms.
Hocam,
Yes,
for adoption, we just can sum up all the degree of freedom we have. They are all same, right? I mean,
yes.
total degree of freedom is
We sum them
79.
up, it is 12. But then we subtracted the constraints because of the joints.
No, what I mean is, hocam, the degree of freedom that we have found after the constraints. I mean, link 2 has 3 parameters, link 3 is 2. Just sum up all of them, so we have the same result as well.
Yes. Well, I guess it is getting late here. We are not going to be able to finish this topic. So let's stop here. Finally, we will come to the degree of freedom equation, which is this Grubler's equation. But let's do it the next time. I will briefly review it and then, well, we will talk about it in a fresh class. Let's stop at this point if you don't mind, okay? Okay. All right.
Hocam,
Yes.
when is your office hour? Or we are
Okay.
just talking to Matt to ask questions?
Okay. I will. I couldn't find a, allocated time for that. I will do that as soon as possible. I'll probably do it before next week. Okay.
Okay, okay hocam.
So let me